In this video, we will be converting between Kc and Kp, the two equilibrium constants. Let's review real quick equilibrium constant expressions for this reaction. We have two different choices. We have a Kc using concentrations. So if we have an aqueous solution and we're given concentrations in moles per liter, we would be calculating out the Kc. Now, if we have a gas reaction where we're given units in atmospheres and we're measuring the partial pressure rather than the concentration of each component of the reaction, we would be using Kp. But what if you're given the Kc of a reaction and you want to know what the Kp would be? Or if you're given the Kp and you want to know how many moles per liter that will be? Well, a lot of it really just depends on if we're creating moles or not, or if we're getting rid of a certain number of moles, and I'll get to that in a little bit. But first, I just want to show you the ideal gas law, because the ideal gas law is basically we rearrange it to get an equation that allows us to solve for Kp or Kc. And it's the idea that Kp is going to be represented in a pressure unit. So atmospheres for us, and Kc will be represented in a concentration unit, so moles per liter for us. R is going to be the ideal gas constant. You've seen this before, 0.0821, and then the units have to be liter atmosphere per mole K. And if we don't use those units of liter atmosphere over mole K, then we can't use 0.0821. So everything has to be in those units, otherwise this doesn't work. Now, temperature is something that you should be familiar with. Temperature is measured in kelvins. And then we have this raised to the power of delta N. What does that delta N represent? This conversion is solely dependent on if we are creating or destroying the quantity of moles in a reaction. So N represents the number of moles, and that delta is going to be the number of product moles minus the number of reactant moles. Remember, delta is final minus initial, and in a chemical reaction, the final thing is the product and the initial thing is the reactant. So how is the number of moles changing? And the reason this has an impact is because when we're dealing with a gas, the number of moles is really what causes the pressure, and when we're dealing with a solution, the number of moles is how we calculate the concentration of a solution. So the number of moles is very, very important, and the change in the number of moles is important. So let's practice converting and solving for Kc. I'm going to rewrite the equation here. So we have Kp equals Kc times R times T to the power of delta N. And in our reaction, we have I2 decomposing into two different iodine atoms. We are given our Kp, which is 6.26 times 10 to the negative 22nd. Now, the units for this aren't atmospheres, but they're represented in atmospheres. This is a partial pressure. They're all partial pressures. So they will be represented in atmospheres. And I'm just going to put that in parentheses so you can see how things cancel out. Now that is going to be equal to Kc times our ideal gas law, or our ideal gas constant, which is 0.0821 liter atmosphere over mole K, times the temperature, and in this situation it is 298 kelvins. That will be raised to the power of delta N, which is the number of moles of products minus the number of moles of reactants, which is going to equal 1. We have 2 minus 1 for that delta N. Now I'm going to basically just condense this down. So we have 6.26 times 10 to the negative 22nd. The units represented would be atmospheres, and that's going to equal Kc times 24.466, and the units are going to be liter atmospheres over moles. The kelvins cancel out, and it's raised to the power of 1, so we don't have to really worry about the power. Now what I'm going to do is I'm going to multiply both sides by 1 over that, or the reciprocal of that. So it ends up being 1 over 24.466. Now the units here flip around. We have liter atmosphere on the bottom and then mole on the top, because if I'm going to multiply both sides by that reciprocal, that will eliminate that quantity. So I'm going to take the other side and also multiply it by the same thing, 1 mole over 24.466 liter atmospheres. And you're going to see that the moles and the liters remain, moles over liters, and the atmospheres cancel out on the left-hand side. And I will show you the cancellation in just a second here. If I do all the math here, I take 6.26 times 10 to the negative 22nd divided by 24.466, and then I get KC is equal to 2.56 times 10 to the negative 23rd. I'm going to report 3 significant digits there. The units represented for KC are moles per liter because this is a concentration equilibrium constant. It's dependent upon the concentrations. So the unit itself is technically not moles per liter, but I want to remind myself and represent this and show that this is a concentration. So here I'm just showing all the canceling out that's taking place. The kelvins cancel out, the liter, moles, and atmospheres on the right cancel out, the atmospheres on the left cancel out, leaving me with moles per liter as a concentration unit. And that's what I have, and that's what I'm solving for, the concentration constant, the equilibrium constant for a concentration. So that is how you solve for KC. In the next problem here, we're going to be solving for KP. So we have the reaction N2 plus O2, and it's an equilibrium creating 2 molecules of NO. The KC we know is 4.10 times 10 to the negative 31st, and this is at 298 kelvins. So I'm rewriting my equation here. We have Kp is equal to Kc times RT to the power of delta N. So I'm solving for my Kp. So Kp equals, I substitute in my Kc, which is 4.10 times 10 to the negative 31st, and I'm going to multiply that by R, which is 0.0821. And I'm going to put moles per liter, by the way, in parentheses for that unit for Kc. The actual units are not moles per liter, but because this is a concentration, it will be represented in moles per liter. And I'm going to multiply that by RT, which is 0.0821 liter atmosphere over mole K times 298 kelvins, because that's the temperature that this is measured at, raised to the power of delta N. So I have 2 moles of product and 1 plus 1, 2 moles of reactants. That means that the number of moles of product and reactant are the same. I'm not creating or destroying moles in this reaction. So we will raise that to the power of 0, which is equivalent to multiplying that Kc by 1. So Kp really just equals 4.10 times 10 to the negative 31st. If we're not creating or destroying moles in this, then the Kp is equal to the Kc. Now I'm going to show you how I deal with those units. So the Ks will cancel out, the kelvins will cancel out, the moles and liters will cancel out, and that will leave me with atmospheres as my unit representing the Kp. And Kp is partial pressures, the equilibrium of partial pressures. So that makes sense that my units should be represented in terms of atmospheres or some pressure unit.